Question 2H3, second edition of Statistical Rethinking. So this is the question, but we are using information from questions 2H1 and 2H2. So just to remind you of what was happening there. So in the first one here, there are two types of panda bear, and we can't tell them apart except for the fact that species A gives birth to twins 10% of the time, and the other times there's just a single baby born. And species B, when it has birth, or when it gives birth to twins 20% of the time, otherwise giving birth to just single infants. Okay. And so we ran through and did that problem, and in this problem we are asked to find what is the probability that if one of the pandas, the panda that we have at hand, gives birth to twins, what's the probability that the next time it gives birth, it will also be twins? In question 2H2, we are instead asked, okay, we found that, or the panda that we had gave birth to twins, what is the probability that it was species A? And we came up with 33, or 1/3. There's a 1/3 probability that the panda we have at hand is from species A. That's what we found in question 2H2. Okay. Just a little bit more about question 2H2. We found, so it's important to understand that the evidence there was that the panda gave birth to twins. That's the only evidence that we have. Okay. And so that updated our prior probability from 1/2 to 1/3. Okay. So now in question 2H3, we are continuing from 2H2, but now that same animal, that same panda that gave birth to twins, gives birth again, and this time it's to a single infant, to a singleton, they're calling it here. Okay. And so we're asked to, again, find the probability that the animal we have is species A. And we're going to do this in two ways. So the way that we've been doing it is we find terms for the prior and the likelihood, and in this case the likelihood would encompass the evidence of twins and a singleton birth, and then we just plug forward with Bayes' theorem. But there's an interesting feature about Bayesian statistics, which is that if I were to run multiple experiments, each time I run that new experiment, so I'm accumulating new evidence, my prior for that Bayesian calculation should be the posterior from the previous experiment, right? And so hopefully this makes sense, because before we see any evidence, we have some probability distribution, some prior probability distribution, and that prior is representing our best guess of the probabilities. Well, after we see that evidence and churn through Bayes, now what is our best guess of the probabilities? Well, that's the posterior. So if we get new evidence, our best guess representing the prior for this new Bayesian calculation that we're going to run through, our best guess before factoring in that evidence is the posterior from the previous experiment. Okay. So the first way that we're going to do this is, instead of using the same priors that we've been using, which is there's a 1/2 probability that we have species A, we're going to instead use the posterior from that previous observation, which was 1/3, as our new prior for this experiment. Okay, and so here I have species A, and my prior is going to be simply the posterior, which is right here from the previous problem, is going to be that posterior, which is 1/3. So this value right here is 1/3. Okay. And then the prior for species B, of course, is just 100% minus the probability that it's species A. Okay. And so now I have the likelihood that I'm considering, which is what is the probability then of a singleton birth given that I have species A? Well, that's already given to us way up there, but there was a 10% probability that species A gives birth to twins, and so that means that 100% minus 10% would be the probability of giving birth to a singleton. Okay, and similar logic here for the likelihood for species B. And now my marginal, again, is just my weighted average of likelihood. So here's the likelihood for species A and the likelihood for species B, weighted by their priors. But these priors, again, are new, right? These are not the 50-50 priors. These are the priors that we developed from the previous experiment. And now I'm just going to run so now I just put these into Bayes' theorem here, and I run through, and we get 36%, right? So my prior that it was species A was 33%. I saw that there was a singleton birth. Species A is slightly more likely to give birth to a singleton baby, and so we see that my posterior is a little bit higher than my prior. Okay. Now, we could do this the other way. We could start with the previous priors of 1/2 and then use as evidence twins and singleton birth. Okay, and so that's what we'll do here, and we're going to get the same answer. Okay, so I'm starting with my old priors, right, that both species are equally likely, 50%. Okay. This is information to us that was given to us in the problem, right, namely that twins given species A is 10%, so the singleton given A is 90%, and similarly for B, for species B. Okay. So these are the two events, but those aren't my likelihoods because the evidence I want to incorporate is both twins and a singleton birth. Okay. So when I want to come up with the likelihood for twins and then a singleton given A, I take the probability of observing twins given species A times the probability of a singleton given A, and then I do the same thing for B. All right, and when we're trying to find joint probabilities, we're just multiplying these two probabilities together. Okay, the reason we're able to, so if that makes sense, you can stop listening. But the reason that we can multiply these together, so in an earlier problem, we had when we were flipping cards, I think that's like question 2M4 to 2M7, there was a similar problem where we flipped one card and then we flipped another card. And in that case, we couldn't do this because those two events were related. They were dependent. So if I had 3 cards and I pulled one out, there's only 2 left. And so what I can pull on that second card was dependent on what happened in the first draw. But in this case, we're assuming that these births are independent, given that we're looking at the same mother. Okay, so once we factor out the fact that this is the same mother giving birth both times, then those births are independent events. Okay. So now I take my marginal, which again is just my weighted average of likelihoods, right? So I weight my likelihoods by the priors. Okay? And now I just chug forward with Bayes' theorem here. And I should get the same answer, 36%, right? So again, what's important here is that when we have independent events, independent observations, independent experiments, we can go through Bayes in either way. We can either throw all of that evidence in at once, which is the approach that we took here in this second approach, or we can go forward one observation, one experiment, one piece of data at a time. Either way is equivalent as far as Bayes is concerned.